going to cover the last part of Chapter 6, focusing on solving trigonometric equations and using trigonometric identities. We'll talk about the identities. You're going to have them all from your formula sheet, which will be obviously a very big helper. But the way we're going to solve these different pieces is just using our knowledge of the unit circle, our knowledge of some basic identities, which we'll talk about before. We'll have the framework of the IB formula sheet. Functions are periodic, so chances are when we're being asked to solve these things, we're only going to be asked to give angles within a certain range or interval. At times, we might need to use our calculator and maybe search for intersections, particularly if we have identities or relationships that are not immediately solvable on the unit circle. That being said, if you see a trigonometric identity question on the non-calculator section, you can rest assured that it's going to be one that's going to be very straightforward. It's a unit circle based or something that directly will fall out of the trigonometric identities. Maybe on a calculator section where you have an identity or some type of trig equation to prove, it could turn out, chances are, as an alternate way of solving it. There's probably always going to be some type of definite way to solve it. But in a calculator version, you always can fall back on an intersection mode to solve some of these equations. For the moment, let's work with some basics. And one of the first things I want you to be familiar with again is the unit circle. And bear with me one second here. You have your red copy. Again, you're not going to have this on the exam. You won't have the cosine of angle t or angle theta equals x, the sine of angle theta or angle t equals y on the unit circle. You will have the identity that tangent of an angle is always equal to sine over cosine or y over x from a unit circle standpoint. Now, I've only drawn a part of the unit circle. There's some pieces or some ways that you're probably familiar with. You might note, hey, anytime I see the square root of 2 showing around, particularly the square root of 2 over 2, I got everything that's showing up in what? In the quadrants. 45 degrees, 135 degrees, 225, 315, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Those things might have been ingrained in your memory, and that's good. All the other angles, particularly the 30 degree, the 60 degree, anything with a pi over 3 or a pi over 6 format, so to speak, those sometimes can be tougher to remember. How do I best memorize the unit circle? And each of you might have a different way of doing this, but if you focus on quadrant 1, here's the technique that I use. For some reason, visually for me, I can see in the first quadrant the y coordinate better than I can see the x coordinate. You might see it differently, I don't know, but just kind of go with that for a moment. And so what I notice is my y coordinate keeps creeping up as I move through the first 90 degrees, or from 0 to pi over 2 in radians, along those critical angles. 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. All the sine values that I see in quadrant 1. But here's the nice thing I noticed. For the first point, and watch how I'm going to write each of these. The square root of 0 over 2. The square root of 1 over 2. The square root of 2 over 2. The square root of 3 over 2, the square root of 4 over 2. You'll notice that what? These values already correspond to what we would have at what? I'm going to use radians at pi over 4 and at pi over 3. The others are going to match the different pieces, but look at the behavior. This is 0, this is pi over 6, this will be pi over 2. Look at the nice progression, the way I've built this numerator. Square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. And if you simplify the square roots that we could clear up, you'd have 0 over 2. There's your 0 value. Square root of 1, 1. There's your 1/2. Square root of 2, square root of 3 over 2. They both show up very nicely. And when you do the square root of 4, square root of 4 over 2, apologize for that as I set this up. 2 over 2, and you walk right into 1. So, quick way to memorize the unit circle, just work in this direction, and then you can apply it to the other places. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, and they walk you right into those values. All right, enough about the unit circle. Let's go back and now start working some of these things. Again, that's just one way to memorize and get a good feel for the unit circle. I find that it works real well for me, and it might for you. So here are the first series of problems that we'll have. Sometimes we might just use to do a little bit of algebra and remember the unit circle, and we'll be good. And so what I'm going to do, just to save ourselves some time, all our answers, just note, need to be between 0 and 2 pi. I'm going to go ahead and work these problems. Sine of t equals 1/2. Again, remember, 0, t to 2 pi. Sine t equals 1/2. What angles have a sine equal to 1/2? Again, you can go off to your calculator and do all this wonderful stuff. We're going to work in radians mode, however. I can translate this into, hey, could you please tell me all the angles on the unit circle that have a y-coordinate of 1/2? Well, it turns out, again, if we kind of remember, 1/2, square root of 1 over 2. That was pi over 6 in quadrant 1. And in quadrant 2, 5 pi over 6. All other places, as we keep moving around the unit circle, we're going to be in negative territory. These are the two answers for that one. Let me come back to number 2 for a moment, but let's look at this one. Sine squared of t equals 1/2. Well, what's that telling us? Well, that the sine of t better equal what? Plus or minus the square root of 1/2. Save ourselves a little bit of time. Most of us should be pretty well familiar with it, given the level we're at. This is telling us that sine of t is plus or minus the square root of 2 over 2. Where do we know square root of 2 over 2? We knew it at pi over 4. And since we're plus or minus, we're going to get an answer out of each quadrant. 3 pi over 4, 5 pi over 4, 7 pi over 4. Let's look at this problem. 2 cosine t equals negative square root of 2. Divide each side. Cosine of t equals negative root 2 over 2. What are we looking for this time? X coordinates that happen to be negative root 2 over 2 on the unit circle. Quadrants 2 and 3. 3 pi over 4. 5 pi over 4. Now, let's do the last one. Sine of t minus pi over 3 equals 0. Now, a good way to work this problem is maybe to think, well, who has a sine of 0? And then we'll adjust off that. So I'm going to do a little quick substitution. I'm going to say u equals t minus pi over 3. And so I'm going to come up with sine of u equals 0. And in this case, what am I going to get? Where is the sine equal to 0? That would be at 0, at pi, and at 2 pi. What do I know about my angle u? Well, it should be t minus pi over 3. So u equals 0 gives me what? T equals pi over 3. U equal pi gives me what? T equal 4 pi over 3. And u equals 2 pi would give me what? T equal to 7 pi over 3, too big. These are the only two answers that I need for that problem. So some basic unit circle got me through all these pieces. Now the second thing we note, something going to require deeper levels of algebra, some nice substitutions, basic substitutions in all honesty, and potentially, not in these problems, but potentially, calculator-based intersection solutions. Again, if you had any of these problems in a calculator aloud, you're welcome to go after that. Chances are, however, they're going to be looking for exact answers. And you probably haven't memorized all the different radian values. I mean, you might know that pi radians is probably 3.14, pi over 2, 1.57, so on and so forth. But I doubt you can recognize all of those. So be careful with the intersection, particularly in these parts where we're looking for real exact answers. So let's work through this next batch of problems. We might have to do some factoring or other things, or substitution. 2 cosine squared plus cosine t minus 1 equals 0. This is a nice factoring version. You can do it with substitution, but I think most of us are good enough that we can kind of see this. 2 cosine t minus 1 cosine t plus 1 equals 0. Let's take a look. It's 2 cosine squared plus 2 cosine minus cosine, there's my plus cosine, and there's my minus 1. This is nice. And what's that telling me? Well, solve it. Cosine t equals -1 on one leg. Cosine of t equals 1/2 on the other leg. What angles do that? Again, remember, we're going to do 0, t to 2 pi. Okay? Who has a cosine equal to -1? The only answer is pi. Who has a cosine equal to 1/2? Well, that would be pi over 3. And in the bottom quadrant, we would have 5 pi over 3. Again, unit circle based, realizing there are different methods of working our way through the unit circle to find these solutions. Sine t plus tangent t equals 0. Well, chances are in everything we're going to be doing, a very straightforward substitution of tangent is going to be required. And so here we go. Remember, sine over cosine is tangent. When I have something like this, common denominator, cosine t. Sine t cosine t plus sine t over cosine t, cosine t equals 0. Sorry that my pluses and the t's look the same, but just kind of bear with me. Here, what can I do? Common factor. Remember, how do you set a fraction equal to 0? Make the numerator equal to 0. I can factor out a sine t from both, and I'll have cosine t plus 1. That's good factoring. That's my numerator, and I can just set that equal to 0. I'm going to look for all the areas where the sine of t equals 0, and I'm going to look where the cosine of t equals -1. Cosine t equals -1 at pi radians. The sine of t equals 0. Pi over 2. Let's think about this. Sine of t equals 0, my fault. We're going to be looking at 0. We're going to look at pi. We're going to be looking at 2 pi. So 3 solutions. Hey, if we got both legs, gave one of the pieces at the same. Just remember, here's our good solution to that. Okay, one more to work with. Going to lose a little space here. Sorry that I wrote so low, so just bear with me. Same concept can be here. I'm going to look just like I did over here with this one, except I'll have a 2 on the bottom. I'm going to have, let me go up just a little bit higher, sine t plus sine t over 2 cosine t equals 0. That's just accounting for the 1/2 here. As before, now I'm going to have 2 sine t cosine t. 2 cosine t is my common denominator, plus sine t equals 0. All of that over 2 cosine t. Again, I'm going to factor. I'm going to be able to take out a sine. Sine t times what? 2 cosine t plus 1 equals 0. Again, I'm going to have a leg of solutions at sine of t equals 0, just like I had before. 0, pi, 2 pi. Now I'm going to look for some solutions at where? Cosine of t equals -1/2. Cosine t equal -1/2. So I'm going to have a lot of solutions out of this piece, right? My cosine, let's use my using circle. I'll visualize it just a little bit. I'm going to be looking for where? An x value of -1/2. Well, companion with pi over 3 is going to be 2 pi over 3. Companion with pi over 3 down here, 4 pi over 3. My other solutions lie at 2 pi over 3 and 4 pi over 3. So I have 5 solutions. My 0 pi and 2 pi, and my 2 pi and 4 pi over 3 that work for this one. All right, so now we've walked through a lot of the basics here. Now, let's go ahead and move forward into use of identities. On our formula sheet, and one of the nice things, we don't have to derive any of these. Sine squared x plus cosine squared x, or sine t plus sine squared t cosine, whatever angle you use is equal to 1. It's the great Pythagorean identity. And remember, where does it come from? It comes from our good old unit circle. I'll use angle t just because that's a letter I've used here and there. We know on the unit circle that what? This point would be x, y. We know via the Pythagorean theorem, if that point's x, y, that's what those coordinates are. So we know that x squared plus y squared equals 1. What's the nice thing that we know on the unit circle? X equal cosine t, y equal sine of t, which walks us directly, therefore, into the Pythagorean identity. Cosine squared t plus sine squared t equals 1. There it is. Chances are you're going to see it written this way. It just reads easier. That's kind of the traditional way in which the formula has always been given. It gives you two other options. Sine squared x minus sine squared x, again, just by subtracting cosine squared from each side. You know how you can write sine squared of x. You know how you can write cosine squared x as 1 minus sine squared x. And the other formulas that you're given that we will not derive, lucky us, representations, and these are straight from the formula sheet. The double angle formulas. Sine of 2x is 2 sine x cosine x. The double angle formula for cosine has 3 potential uses. And you'll see they all work. You can choose, based on the problem that you're given, which one you're going to want to work with going forward. All right, so let's go ahead and work these last few problems. I'm going to do 1, 2, 4, and 5. So my first problem is giving me 1 plus sine t equals 2 cosine squared t. I'd like to get everything in the same trigonometric family, at least. Nice thing is, we'll notice for the first few problems, I already have all the angles the same. That's another thing that I'd like to work my way into. Well, what can I use? Well, I can see a cosine squared respected down here, but that's not very pretty because I'm going to have to change my angle if I decided to substitute there. But what's another nice feature I use? I know at least what cosine squared is, so I could do the following. 1 plus sine t equals 2 times 1 minus sine squared t. 1 plus sine t equals 2 minus 2 sine squared t. Bringing everything over to the left side, 2 sine squared t plus sine t minus 1 equals 0. And I can factor this. 2 sine t minus 1 sine t plus 1 equals 0. Let's check it out again. 2 sine squared plus 2 sine t minus sine t. There's my plus sine t. Minus 1 equals 0. Great. How do I solve it? Sine of t equals negative 1. Sine of t equals 1/2. Sine of t equals negative 1. 3 pi over 2. Sine of t equals 1/2. That lives at pi over 6 and 5 pi over 6. Pi over 6, 5 pi over 6. There's my answers. 4 cosine squared t plus 6 sine squared t equals 5. This one's a little bit ugly. It takes a little bit of eyeballing, but think about a nice way to handle and to combine these things. Well, here's an option. 6 sine squared t is the same as, watch what happens, plus 4 sine squared t plus 2 sine squared t equals 5. I just broke this up, 4 sine squared, 2 sine squared. What's wonderful about this? This becomes 4 cosine squared t plus sine squared t plus 2 sine squared t equals 5. In parentheses, the Pythagorean identity, this becomes 4 plus 2 sine squared t equals 5. 2 sine squared t equals 1, subtracting 4 from each side. Sine squared t equals 1/2. sine of t, sine of t equals what? Plus or minus the square root of 1/2 equal plus or minus square root of 2/2. And we're good on the unit circle. We know that's the one that bounces back across the pi over 4s. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So this one a little bit tougher, but again, a Pythagorean identity really bailed us out quite nicely. Sine of 2t minus 2 sine squared of t equals 0. Attacking, anytime you see a double angle, try to eliminate it. It's going to help you. You want everything in terms of just one angle. So I want to rewrite sine of 2t. Fortunately, it's a sine. I don't have to choose what option I'd like to use. I'm sorry, let me go up a little higher where you can see the identity. Sorry about that. Fortunately, since it's a sine double angle, I only have one rewrite capability. 2 sine t cosine t minus 2 sine squared t equals 0. I simply did my double angle formula for sine of 2t. And there you can see it again. Sorry about that, as I forgot to move my camera. Common denominator, 2 sine t, what's left? Cosine t minus sine t equal 0. See if we trust that. 2 sine t, take them out of both. Cosine t left, sine t left. Good. Okay, this is again sine t equals 0. Where's that happen? T equals 0, t equals pi, t equals 2 pi. Cosine t minus sine t equals 0. That's going to require, this is kind of a funnier one usually for how we solve things, but that's going to say my cosine of t must equal my sine of t. Where does that happen? Well, interesting enough, it's in the places where you see equivalency, right on that lovely pi over 4 splits. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So some pretty neat stuff. Lots of angles that satisfy that particular problem. One more to work with. And again, we're going to do more practice. Didn't do any specifically with these examples where you're going to use your double angle off of cosine, but we'll do some more of those. We'll talk about it in a second, but let's work problem number 5. 4 sine 2t equals 5 cosine t. Again, your hand is kind of forced. 4, 2 sine t cosine t equal 5 cosine t. 8 sine t cosine t equals 5 cosine t. 8 sine t cosine t minus 5 cosine t equals 0. Common denominator of this, or common factor, excuse me, I'm going to move over here where I got a little bit more space. Cosine t, 8 sine t minus 5 equal 0. Cosine t equals 0, where does that happen? It happens at pi over 2, 3 pi over 2. 8 sine t minus 5 equals 0 requires sine of t equals 5/8. This is going to be an example where, again, you'll have to go to your calculator. You're going to return, this is not going to be anything that sits on the unit circle, but you'll return answers in quadrant 1 and in quadrant 2, just based off, in this case, what would you do? You'd wind up running an inverse sine. You would solve sine of t equals 5/8. You'd run your inverse sine of 5/8. Come back with an answer via the calculator in quadrant 1. Apply that answer in your reference concept to get your angle in quadrant 2. All right, so there's one more problem left to do. It's kind of an interesting one. Let me get a blank piece of paper where I can work it. The problem that you see is number 3, which says cosine t plus 1 equals sine t. Now this is kind of an interesting one. You don't really have, there's no identities that are out there. You got a kind of a mixed sine and cosine. How would you handle one of this? Well, there's some intuition that you could use. If you recall, the cosine is the x coordinate. The sine is the y coordinate. And so what's it saying? Well, if I talk unit circle, I'd be looking for the places on the unit circle that hold the following. X plus 1 equals y. X plus 1 equals y. And if you think about it, there's not a lot of spots on the unit circle that you can kind of come through and automatically think about where that's typically the case. But let's come back and think something through. Think about spots that you do know on the unit circle, particularly the ones that I'm highlighting right here. 1, 0, 0, 1, -1, 0, 0, -1. And something you might notice is that's a safe place where that happens. The coordinate 0 for x and 1 for y exist at what? Pi over 2 radians. Interesting thought process. And there's a way to walk into a solution just like that. Now you might think, oh, maybe there's some other values, maybe where x is positive over here and negative over on this side, that maybe something will get pulled off. But let's use some, going beyond intuition, let's use a couple more things. What do we know in this world? We know that x plus 1 equals y is a true statement. We also know, let's take a peek at something else that we know in this instance, because it's on the unit circle. We know that x squared plus y squared equals 1. And so we're getting some interesting pieces that come back and forth for us in this scenario. If this is true, because that's the equation we're trying to solve, if you think about it, this has to be true on the unit circle. The implication that comes across to us then is that x squared plus y squared, and what's y squared? Well, unit circle language, x plus 1 squared equals 1. What's that telling us? Well, x squared plus 2x plus 1 equals 1. That's telling us that 2x squared plus 2x plus 1 equals 1, or x squared plus 2x equals 0. 2x, x plus 1 equals 0. Where do our solutions come? Where x equals 0 and where x equals -1. And we can translate that, well, when x equals 0, where are we on the unit circle? We're at 0, 1. When x equals -1, we're where? At -1, 0. Does the relationship hold for those 2 points on the unit circle? Absolutely. And so what are our angles that solve this? It would be t equals pi over 2 and t equals pi. So this was a kind of use some intuition. Again, this is a great one. Hey, run to your calculator or whatever. Unfortunately, your calculator, you're going to have to translate pi over 2. You're going to have to recognize 1.57. Pi, for another answer, you'll probably recognize -3.14. But again, sometimes those numbers don't roll right off the top of your head. But what we did here is we took advantage of the unit circle and some basic knowledge, realizing that cosine could be x, sine could be y, knowing that on the unit circle, x squared plus y squared equals 1, we have two equations. We can substitute for y as x plus 1, put that into our Pythagorean identity, and run home the rest of the way. Interestingly, what did we do? We identified the x coordinate on the unit circle, and then just worked our way through to figure out, okay, well, what's the associated y coordinate that can work with that as well? So I hope this helps give you a good feel for how we work through a series of these problems. It's a lot of work here. It's not insurmountable by any stretch of the imagination. And we'll have you work on some practice sets to get fuller and more acquainted with this.